Hi everyone, and welcome to Eric's Electronics Workbench. In this video, we'll take a look at this military model TS-352AU multimeter and what's required to modernize it with some commonly available batteries, such as AAA and AA batteries, instead of the long since obsolete and discontinued batteries that the military originally used. And of course, there were a couple surprises that I encountered along the way, and I'll explain all of that in this video. So let's get started. Okay, on the bench today we have this military model TS-352AU multimeter, also known as an ME9HU multimeter. You ask, well, why are there two different models for the same meter? Well, the TS-352AU describes the complete setup with the meter and any accessories like test leads and so on, where the ME9HU is just the meter by itself. Okay, so you'll often see these referred to under both models. It's really one and the same. So let's take a look at some of the functions and features and the controls that the meter has. We'll start over here with the test leads and also just in the front cover. The cover itself has a nice storage compartment, slides up, and some technical specifications and ratings that are given in the front, on the inside of the front cover. So set the cover aside, and on the test leads themselves, something to note is that this uses the older style pin type plug that goes on the end of the test lead. Okay, so the other end of this particular test lead set has the alligator clips that unplug, and then you have the probe itself, but the end that goes into the meter has the early style pin type plug. So if you have to purchase a set of test probes for one of these meters, keep that in mind. Compare that with a modern style test lead set that has the safety shielded banana jacks that are very common on modern meters, but again, a probe set like this would not work for this particular meter. So let's take a look at the front of the meter and the controls that it has, and also some of the connections and how you would actually go about using the meter. Okay, so looking at the front panel, we have a function switch over here, which has the 20,000 ohms per volt direct and reverse. Reverse is just the same as if you were to switch the test leads around for the polarity. It has 1,000 ohms per volt DC, DC current, ohms, and then AC volts. And AC volts is at 1,000 ohms per volt. Okay, and we'll talk about the ohms per volt and what that means in just a moment. In the middle here is the knob to zero out for the ohms zero setting when you short the test leads together, which basically is compensating for the battery voltage variations as the battery's age. And over here, this range switch has the ohms or resistance ranges, resistance times 1, times 10, 100, 1,000, and 10,000. And then the amperage or DC amp scales down here, ranges I should say. We have 2.5 and then 10 amps, both at the same position. And the difference between those is selected on where the probes are plugged in up here. We'll get to that in a moment. 500 milliamps, 100 milliamps, 50 milliamps, 10 milliamps, 2.5 milliamps, and then 250 microamps. So something to keep in mind with one of these meters is that there is no overload protection in the meter. And of course, a meter like this is manual ranging. It's not auto ranging like a modern digital multimeter would do. So if you were to plug something in on the 2.5 or 10 volt jack over here and apply, 500 volts or 250 volts, something like that, or even up to 1,000 volts, and you were down here on one of these lower ranges, you'd very likely damage the meter. So keep that in mind when you're using this. There is no protection. There's no fuses in here on the DC current. If you apply more than 10 amps, there's no fuse. There's really no safety measures in one of these meters. It's up to the person using it to understand what its limits are and how to properly connect it. Now down here there's a case ground, you'll see that right here. That's just a connection to the base part of the chassis or the case, which is metal. This top cover, I'm not sure if it's Bakelite, but it's a plastic type material. Not really even plastic, but definitely an insulated type material, because all of the electronics on the inside are mounted on the back side of this front panel. So this is an insulating type material. So the case ground is just a convenient way to tie just to the case. This case ground is not the same as where the negative test lead goes. We'll get to that in a moment on where that actually plugs in. So if you have your test leads, the negative test lead, or the black test lead, for everything that this meter is capable of doing remains right here in the jack that says ohms, and then negative DC plus minus AC. So it always remains there. This never leaves this connection right here. Okay. Now, the positive test lead moves around quite a bit on this particular meter because the voltage ranges and some of the functions that this meter can do depend on where this lead is plugged in. So if you look down the side over here, it says 20,000 ohms per volt, and then it says 2.5, 10, 50, 250, 500, and 1,000. So if this is brought over here to 20,000 ohms per volt, normally you put this on direct reading, and let's say you were expecting to read something, perhaps 25 volts, 40 volts, something like that, something under 50 volts, you would plug this in like so. Now, if you apply more than 50 volts, this would indicate beyond full scale, and if it's extremely beyond 50 volts, there is a possibility of damaging the meter movement. So again, keep that in mind. If you have, let's say, 1 volt, 3 volts, 5 volts, something very low, and you're on the 50 volt setting, you'll only get a very small deflection, very difficult to make any meaningful or accurate reading. So if that happened, then you would want to move this down to 10 or 2.5 as appropriate. If you have no idea what the voltage is, you would start at 1,000 and work your way down, okay? So it's, again, a manual ranging. It's up to you to select the appropriate range and always start at the highest range and work your way down if it's unknown. So we have 20,000 ohms per volt and 1,000 ohms per volt. So again, 20,000 and 1,000. And what does that mean? Well, it's basically telling us the input resistance that the meter has. So if you look with 20,000 ohms per volt and we have 50 volts, okay, you just multiply 50 times 20,000. So 50 times 20,000 is 1 megohm, okay, or 1 million ohms. So that's telling us that on this connection right here, between these test leads, we have 1 million ohms of resistance that this meter would apply, or that the circuit that you're testing would actually see. It would see 1 million ohms. Pretty high, not as high as a lot of modern meters, okay, but fairly high. That resistance goes up 250, 500, 1,000. Take those numbers, multiply them by 20,000, you'll get the resistance of those ranges. Something lower is obviously under 1 megohm. Now you can actually verify that if we unplug those. I'll grab my other meter over here. So if you take digital multimeter, go into there and probe into there like so. So again, we're on the 50 and the common up here. And we can see that the meter is in fact indicating right at 1 megohm, okay? So 1.001 and then megohms. Put the glare off of the screen there. All right, so exactly right on 1 megohm. So on the other side, we have 1,000 ohms per volt. So if I put the function switch down here in the 1,000 ohms per volt DC, or again, AC volts is taken over here, same 1,000 ohms per volt. If we plug this in up here, we'll use the 50 volt as an example again. 1,000 times 50 is 50,000, and in fact we do see that on the meter. 50 k ohm. Okay? So when you see the ohms per volt, it's just a way of telling you what the input resistance of the meter is. Now, why is that important? Well, the higher input resistance over here, this meter burdens or causes less, you could say, interference, less load, however you want to look at that, on the circuit that you're testing. And that can be very important if the circuit that you're testing has a very high impedance or high resistance. If you use the 1,000 ohms per volt, it will load the circuit down and drag or pull the voltage down, and you'll actually get a substantially lower voltage reading than you would if you use the 20,000 ohms per volt. Now, it's important to mention that this meter has no active circuitry in it, okay? There are no vacuum tubes. It's not a vacuum tube voltmeter in any way. There's no transistors. There's no integrated circuits. The only thing inside of here is a whole bunch of resistors and 2 diodes, all right? So the diodes are used for the rectification on the AC volts. and everything else is done with resistance, voltage dividers, and so on. So pretty amazing what the meter can do, given that it's quite simple actually inside as far as the electronics. Quite reliable as well. Which brings to the next point with the batteries that we'll be talking about on this meter. The batteries are only used for the ohms function, all right? So all of the other functions that this can do, DC volts, AC volts, DC current, in no way do they use the batteries. So it makes this meter quite reliable because you're never going to have dead batteries for any voltage readings or current readings, and it makes the meter something that if you leave the batteries out of it and you just go to grab it, you can always rely on it to use for voltage and current readings, which is, you know, a nice feature. Nice to have that you don't have to have a fresh set of batteries in it to be usable. So to finish talking about the various functions on the front panel, we have the ohms, which you would select over here like that, and you have the negative test lead remains on this jack, and the positive test lead goes over here, and then you have resistance, R times 1, 10, 100, 1,000, and 10,000. And if you want to measure current, you place this on the DC current. Negative test lead is over here. You have positive current and then positive 10 amps only. So starting over here, if this switch is on the 2.5 and 10, let's say you don't know what the current is, you would want to start with the highest current range, which would be 10 amps. You would place the negative lead here, of course, and the positive would be in the 10 amps. If you got very little deflection, then you would know to step down. You would put the positive test lead here. For all of the other current measurements, it would remain in this jack. So from this jack here, you would then have 2.5 amps. You come down here, 500 milliamps, 100 milliamps, 50, 10, 2.5 milliamps, and then 250 microamps right here. These numbers are full scale readings, so 2.5 milliamps, that's 2.5 milliamps full scale. Again, any of the other things on here with resistance, voltage, it's always referring to full scale deflection on the meter. Now at the top, I'll move this down just a little bit. This is optional. Not all of these ME9HUs have this, but on the top of here is a high voltage multiplier. We have a 5,000 volt input over here, which is actually just a standard banana jack input. You do want to use a high voltage probe, something that's rated for up to 5,000 volts. Common test leads are not rated that high. They often stop at 1,000 volts, so be cautious on what the test leads are rated, but you would need a special high voltage probe. So we have 5,000 volts over here. It is rated 20,000 ohms per volt, so very high impedance. This is basically a very high value resistor that's inside of here. And on this side, if you do want to use this function, it says connect to 2.5 volt jack. So you have a short jumper that goes from here to right here. Okay, so your negative probe again is on this jack. Your high voltage test probe is here, and this is jumped over to the 2.5. I'll zoom into the meter scales and point out something here. Go down like that. That's a very nice meter, very easy to read. Colored scales. We have the blue, black, and the green colors, so very easy to read. If you are using the 5,000 volt range, even though it's on 2.5 volts over here, you're actually reading on the DC volts where it says 5, 4, 3, 2, 1, and then of course 0. Those become 1,000, 2,000, 3, 4, and 5,000. So you do need to change which scale. You're not reading the 2.5 to 1.5. So just a slight difference on which scale you read on for the 5,000 volts. But any of the other ranges, for example, if you're on 50 volts over here, then you read on the 5 becomes 50, 4 becomes 40, 3 would be 30, and so on. If you're on 500 volts, then the 5 is 500 volts, 400 volts, 300 volts, and so on. 2.5 volts here is very easy because that's right at, you have 2.5 to 1.5, you're reading that directly. So some of these higher ranges, you're just basically adding some zeros to the numbers that are on that scale. For the resistance, for example, R times 1 over here, you're reading directly where it says ohms in green on the top, so we'd have 0, that would be 5 ohms, 10 ohms, 20 ohms, and so on. If this is on 10, you're just multiplying this, so this is no longer 5, but 5 times 10, 50, 100, 200, and so on. If it's on R times 10,000, well, then you're just adding more zeros as we go along. Very straightforward and easy to use meter. Very rugged. It's nice because it can withstand rain, dust, harsh conditions. These were made to take a lot of abuse in the field, and it has a gasket around the edges. It keeps the water out. Certainly rain resistant, and again, very, very rugged meter. The meter movement itself is very rugged and very well made. So if you're following along and working on one of these meters, please know you do so at your own risk. The batteries that I'll be discussing and using in this video are lithium batteries, and lithium batteries can be very dangerous, very volatile if they're not treated correctly, not handled correctly. You don't want to cause any short circuits, damage the battery in any way. So again, if you're following along, you do so at your own risk. Just know the dangers, and if you don't understand something about the circuitry or the batteries or what's involved, please refrain from working on one of these meters until you fully understand all the details and what's involved. So again, you do so at your own risk, and just be safe. So let's take a look at what the battery requirements are for this multimeter. So the batteries are only used for the ohms functions, R times 1 through the R times 10,000. The AC volts, and DC current on this multimeter do not require the batteries to be installed, so the meter is basically powered by the circuit under test. But again, on ohms, you do need to have the batteries installed. So we'll take a look at what batteries are required. Flip the meter over. And battery cover is on the back here. There's 2 screws that will open up. Like so. Cover comes off. Zoom the camera in a little bit closer here. Okay, so on the inside of the battery cover, we can see there's a diagram, and on the top here we have a BA30 1.5 volt battery. Well, BA30 is a military designation for a D cell, typical 1.5 volt D cell. But down here we have a BA31, 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 and 4.5 volt. Now, what is a BA31? Well, it's an obsolete, no longer available battery. You can see the terminals on the side right here, and it says battery links, and which this meter actually had stored away inside of it. It did have the original links right here, pack, some metal links, the nuts that went on the end of the battery terminals. Nice to have those, but the batteries are not available. So the question is then, what can we do to replace these 3 batteries? Well, first of all, if you install the D cell battery up here, you'll find that most of the ohms functions actually work. Okay, so with just the D cell battery installed, the R times 1 through the R times 1000 ranges will function correctly. Okay, so just one battery will get you some functions out of here. But the R times 10,000 requires all the batteries to be installed. All right, so these 3 batteries plus the D cell all must be installed for the highest ohms function or ohms range to function correctly. Well, if you look here, we have 4.5 volts. They're in series, so 4.5, 4.5, 4.5, and then 1.5. The voltages are all adding up. So my first thought was a little holder like this that is for AAA batteries, okay? And it holds 3 AAAs. Wire leads come off, so these AAAs are in series. And that fits in there really nice, no problems like that. And a little piece of foam over the top. The battery cover would go on there that would hold that right into place. So we have 3 of those. I thought, well, that'll work really well. That, okay. And that would certainly get us with 1.5 volt batteries all stacked up in there. You know, 1.5 times 3 is 4.5, and then again you're doing that 3 times. We're right back to the voltage that the meter expects, and we have our D cell in there, and we would be in business. Well, if you want to use original alkaline type batteries, that would be perfectly acceptable. That will get you exactly the voltage that the meter expects. Put a D cell in here. the D cell batteries in here. I would recommend the AAAs. AAs will be a little bit larger. I haven't tried that. They may fit, but the current requirement is very, very small. So I think the AAAs would be fine if you went with alkaline. However, personally, I've had very poor luck with alkaline batteries. I find that they leak and that they just don't have a very long shelf life. Not something that I wanted to put in the meter. So I prefer in applications like this where you have the meter is in storage, it's not seeing necessarily daily use, it might sit for a few weeks and then you use it again. You want something that's reliable. You don't want it to leak in here. You're not looking at the batteries every day, so you want to be able to trust them that they're not going to leak. I have had very good luck with lithium batteries. So, for example, right here, we have these Energizer lithium type batteries right here, lithium. These are not rechargeable. Okay, these are not lithium ion. These are just lithium batteries, AAAs. Okay. And in no way is Energizer a sponsor for this video. These are just simply batteries that I have found work very well. These batteries have what's advertised as a 20-year shelf life and that they are claimed to be leak-proof. I have never had one leak, and I find that they do, in fact, have a very, very long shelf life. I use the lithium 9 volts in my meters. This Fluke meter right here. I use the lithium 9 volts in here. They work very, very well. And again, you can trust them that they don't leak, which is nice because they tend to be in the meters for a considerable amount of time. The lithium batteries have a much higher capacitance than the equivalent sized alkaline type batteries, which is another advantage. So a couple problems come up if you use these lithium batteries in here as this is laid out, where you would have the 3 batteries and 3 and the 3 in series. Okay, there is a problem with that. I'll get to that in a moment. There's also a problem up here where you have the D cell battery. There's no lithium D cell battery, okay, 1.5 volt. There is a D cell size battery that's lithium, but it's a higher voltage, okay? It's not 1.5 volts. You cannot use that in here. If you put a higher voltage, something well above 1.5 volts in here, it'll just peg the meter over all the way on the ohms function and you won't be able to zero it. It won't work correctly. So what's the workaround? Because again, I want lithiums in all of the positions in here. So if you want to go with the lithium batteries, you can get what's called a D cell adapter, all right? So this is basically, looks like a hollow tube. You can see there's nothing inside of it. It has a little button on the end right here, which is equivalent to the button that you would have on the end of the battery. So you take an AA battery, so this is an adapter for D cell to AA. So this is an AA lithium. Just drops in, snaps in place, which is nice, it doesn't fall out. So again, that button end right there is the same as the original button end of the battery. This is the flat side of the battery. So now we have a lithium D cell sized battery that will fit in here. Now you say, well, the D cell was a much larger battery. This is too small, an AA, this won't work. Well, yes, it will work. The AA lithium has a very high capacity and will outperform the original D cell that was intended to be used in here years ago, all right? So this D cell just simply goes in here like so, and like that. And that's all there is to it. So we have an AA in here in place of the D cell, and that'll work very, very well. Now you say, well, what's the current requirement? What, will that battery actually hold up? And again, yes, it will. When this is being used in the ohms function, okay, the R times 1 draws the most current. And the most current happens when you short the test leads together, which you would do when you're zeroing out the meter. So on the R times 1 scale, when you short the test leads together, 60 milliamps flows from this battery. So 60 milliamps, well within what the battery can handle, not a problem whatsoever. So this battery will have a very, very long service life in here and a very long shelf life. So the actual current draw on these batteries, R times 1, just flip this back over here just a moment. See the front panel again. So down here where we have the R times 1, again, R times 1, test lead shorted, 60 milliamp draw. On the times 10 range over here, when you short the test leads, you'd have a 6 milliamp draw. The times 100 range is 600 microamps, and the times 1000 range is 60 microamps. Very, very small amount of current that actually flows. And again, that's only when the test leads are shorted. When you're taking resistance readings and let's say you're on the R times 100 over here and you have a 1K resistor or a 2K or something like that on some of these higher ranges, well, you have much lower current flowing even then. So the highest current flows when the test leads are shorted. When the test leads are open or this is not in the ohms functions, there's no current whatsoever flowing from those batteries. So they're just sitting in there, they're not doing anything. So you can leave this in the ohms positions here. If the test leads are open or not connected, no current will flow. So that leaves the 10,000 times 10,000 range over here, and that range requires 60 microamps from the batteries all in series. Okay, so again, very, very small current draw, and that would be again with the test leads shorted. But another problem does come up. So flip this back over again. So we've been talking about 1.5 volt batteries, but in fact, the lithium batteries are not 1.5 volt. They do call them that, but that's not actually what the voltage is on them, particularly when they're new. Let me grab my meter here. Get this set here. You can see that, yep. So here's a brand new AAA lithium. Okay, and if we take a look at the reading here, you can see it's not 1.5, it's actually 1.8. Okay, and every lithium AA or AAA that I've received that's brand new out of the packaging is always 1.8. Okay, so the 1.8 actually causes a problem because it, again, not 1.5. So if you take 1.8 volts and you stack up 9 batteries in here, okay, we had 3 here and 3 and then 3 in our holders, you come up with 16.2 volts, okay, across here. And that's too much. The meter itself, you cannot zero out the ohms function if you put all lithiums in here in all of those positions. It just pegs the meter all the way over and you just can't bring it down with the zero function. However, if you put 8 lithiums in here, so 3 and 3 and then 2, okay, in our holders, you'll come up with 14.4 volts. Okay, so 1.8 times 8 is 14.4, and that actually will function perfectly. The 14.4 is well within the range of what this can zero out in the ohms function. And actually, it's that voltage plus this D-cell voltage, which again would be very close to 1.8 when it's new. When you put a little bit of use on the lithium batteries, you'll find that they drop to about 1.7 to 1.6, and they'll stay around that value for a very, very long time, particularly with the low use that this meter has. A brand new lithium D-cell, AA up here in our D-cell position. Move this back over again. When you first install this, 1.8 volts across here, you'll find that the meter doesn't quite zero out, and if you give it just a minute or two, that 1.8 volts will drop down to about 1.7, and then the meter will begin to have a fall within the range that you can actually zero it out. So the lithiums work very well in here, but we won't be able to use all the positions when these are in here like this. We'll put 3 lithiums here, we'll put 3 lithiums here, 2 lithium batteries in this position, and what I will do is on the holder, because I already have these, I'm going to just put a wire from one end to the other, basically just, you know, shorting out, if you want to say that, or jumping across so that there is no battery. And by doing that, it'll be a reminder not to install anything there. You could also get a holder that just holds 2 batteries, but like I say, I already have these, so I'm going to use them, and I'll just solder in a little jumper wire, go from the spring over to the little button end on the side there. So that'll eliminate the one battery, and it'll give us the correct voltage, and it'll work very, very well. So when you have the batteries installed, if you measure the total voltage that the meter can actually handle for the ohms function, the actual voltage range is 13.7 to 16.9 volts, okay? So that 13.7 to 16.9 volts, that's these AAAs that we're using and this D cell, now turned into an AA up here. If you measure in series all of this voltage, the total that you can apply to this meter and be able to zero out the ohm function is, again, 13.7 to 16.9. So there's not a lot of different combinations that you could really use. For example, stacking up some 9-volt batteries in here won't work. You know, 2 9-volts, you have 18 volts, too much. That won't work. If you put a 9-volt and you try and combine a 9 in series with some AAs, there really are no other combinations that work and that will give you the voltage that we need for this to function correctly. So from my experimentation with this seems to be the best way to go with the conversion and to get batteries in here that will actually function and make this meter work the way it's supposed to. All right, so the next thing that I need to do is to actually make the wiring connections in here, solder these, use some heat shrink, join these all in series. So this red lead right here is the positive input from the batteries, so this red lead will join here. I'll get rid of the original wire and just make the connection right on this terminal. The black lead then goes to the red, the black over to red, and then the final black lead right here goes where this green wire attaches, all right? And I'll be back once that's done and we'll check that out. Before I stop at this point, I can actually demonstrate with this one battery installed, we can see some of the ohms functions that do work. So move those out of the way. Flip this back over. Prop this up here. It's got quite a bit of glare on that front there, like that. You can see that okay. Zoom in a little bit closer there. So again, we have the D cell installed, or our D cell, AA turned into D cell. So put this over to ohms, R times 1. Grab the test leads here. So the negative test lead there, positive test lead over like that. So with these leads shorted together, you can see this comes all the way, it actually goes past the end there, and you turn this down, and this is what is important to notice or take note of. When you have that lithium in there that is the higher voltage, that lithium is probably very close to 1.8 or just slightly under right now, certainly at least 1.7. This is turned all the way down on the adjustment, and you can see it's right at 0, right about there. If I turn this clockwise, you can see it goes off scale. So what that means is that as that battery ages, you will be turning this further and further over. Of course, as the battery ages and the voltage drops, that'll come down. There's a long ways off from that. That battery will last a very, very long time in there. But again, when you first put the lithium in there and it's very close to 1.8 volts, you'll find that even when this is turned all the way down, this will be off scale. It'll be up too high. But if you short the leads together, put on R times 1, that draws the most current, give it a minute or two, things will settle in, and then it'll come into the range that you can actually zero it. So you can see it's right on 0, no problems there. If you go to R times 10, it's very close. Times 100, a slight adjustment there. R times 1000. It is normal to need to re-zero this on each of the ranges. It just is a side effect of the different tolerances of the resistors that are part of that circuit in there, slight differences. So every time you change this, a slight readjustment of that is normal. And then because our other batteries are not installed yet, if you go to the R times 10,000, you can see it does not function. No position of this knob will cause any change whatsoever, but that will be corrected once the other batteries are installed. So that is what I will work on next, and I'll be back as soon as that is done, and we'll take a look at how the meter functions. Okay, the wiring is now complete for the AAA battery holders, and you can see the AAA lithiums are installed, so there's 8 of those. The AA in the D-cell adapter that we previously looked at is up here. So the AAAs are about 1.8 volts each. We have 8 of them, so that's 14.4 volts. So let's make sure we have that. We'll go from the positive to the negative, and we do see that, 14.43. No problems there, that looks very good. This AA up here with a little bit of use on it has settled in 1.76. So if we take the 1.76 and add to the previous reading there, we do come up with 16.19, so that looks very good. So that's the total voltage, 16.19, and that's used on that highest ohms range. Now remember that total voltage that the meter can withstand and still zero out on the highest ohm range is 16.9, okay, 16.9. So again, we have 16.19, and a 16.9 is the highest. So no problems there. The meter shouldn't have any issues whatsoever. The lowest that this can fall to and still be able to zero out is 13.7, okay, 13.7. So that's the usable range that the meter is able to tolerate and zero on the ohms setting. If you're above or below those values, then that ohms zero adjust knob, when you turn that, you just simply won't be able to zero the meter anymore, which then of course makes the ohm readings inaccurate. So I will get the cover installed on here, and just to secure the batteries, these little foam blocks will go on top of each set of batteries. That'll hold those securely in place. The cover will sit in there, screw down with the 2 screws, and will be in very good shape. Shouldn't be any problem whatsoever. The battery box in here is all insulated, so if these were to move around just a little bit, there's nothing that they could short against. They can touch against the edge or so on. Nothing can short out. The wiring is secure, so we're in good shape. One thing I should add, this one, because again we're not using the 9 AAAs, we're going with the 8 because the 9 would give too much voltage. This one right here has been bypassed with a straight piece of wire, so it's just acting as a short, and that cell is not installed. Be aware these plastic battery holders melt very easily. So when I soldered this wire, this little jumper wire in place in here, it basically started to melt the plastic very quickly, and you have to work very, very fast on the soldering. A workaround on that, and probably a better recommendation rather than soldering the wire, would be to use a dummy cell. If you look online, there are numerous battery supply places that will sell dummy AAAs and dummy AA batteries as well, but in this case a AAA battery. They're basically a dummy cell. They're shorted from end to end. They're often used in flashlights. If you retrofit a flashlight to an LED version, oftentimes you don't need the total voltage that the old cells added up to, and you can add a dummy cell in. So that's where they're often sold. So if you look online at battery replacement, battery supply places for flashlights, you'll see dummy cells, and a dummy AAA rather would be probably a better solution here rather than trying to solder. So I'll get this reassembled, and we'll turn the meter over and hook up some resistors and see how it performs. I'll be back in just a bit. Okay, I have the ME9HU multimeter in position so that we can try out some of the resistance measurements, and I've grabbed some random resistors so that we can try out the different ranges, resistors that are appropriate for each of those ranges. I'll start with measuring the resistor using the Fluke 85.3, and then see what its value registers as with the digital multimeter, and we'll compare that to how this meter performs and see how accurate it is. So right now this meter is zeroed out. It's in the R times 1. You can see if you turn the zero adjust, you can swing above and below 0. So that's right there. It looks like that's right on 0, so that's looking very good. So the first resistor is a 15 ohm. All right, 15 ohms. That's what it's marked as. So let's see here how it actually reads. So 15.1. Okay. 15.1. All right, that's looking very good. So on the R times 1, we're reading across the top. That's 0, 5, 10 ohms, 20 ohms. Of course, 15 is right in the middle, and it's exactly where it's indicating. So that looks very good. No problems there. So the next resistor is, let's see, 150 ohms. All right, 150 ohms. Yep, 150, no problems there. Matches up. So we'll go to the next range, zero the leads together, short the leads I should say, and zero the meter, it's right on 0. Connect the resistor like so. So we're on the times 10 now, so that's 0, 50, 100. This is 150 ohms, so we're right halfway between the 10 and the 20. Looks very good, maybe just the needle width past that halfway mark. Not a problem. There is a percent error that is expected with these meters, so that's looking very good. Not a problem whatsoever. It's really, really close. Analog meters always have some error that you have to account for, which is actually what's printed in the top cover that's over there. It talks about the percent error that you can expect. Okay, the next resistor is marked 4,000 ohms, 4K ohm. So 4.085. So almost 4.1, so 4.08. All right. So we'll go up to the next range, short the leads together, right on 0, no problems there. So that's looking very good. We've got, this would be 3,000 because it's on the times 100, so 3,000, and that would be 5,000. 4,000 is the larger tick mark right in between, and we can see it is just slightly over, but it did measure almost 4.1, so that makes sense. That is a very reasonable indication right there. No problems with that. Very, very close. All right. So the next resistor is a 50K ohm. All right, 50K ohms. Let's see how it reads on the digital multimeter. 50.2 K ohm, all right. Make sure it's zeroed out. There, like so, all right. So 50 K ohms. That's looking very, very good. So this is on the times 1,000, and we're at 50, so that's 50,000. And the needle is pointing exactly at 50. So very, very good. Really looks like it's quite accurate. Really good. And the final resistor is a 500K, half megohm, okay, 500K. So we'll take a look here. This is now in megohms over here and 0.505, so matches up, no problems with that. Okay, so this is the final highest range right here, R times 10,000. So the leads are shorted, zeroed out. This is using all of the batteries now, okay? So all those little AAA batteries in there, plus the AA in the D cell position. So we're looking for, it's 500K, and we do see that. It's right on the 50 times the 10,000. Looks very, very good. No problems whatsoever. So it really looks like this meter is quite accurate. All right, so I'm going to do a demonstration, and I'll get things set up here in a moment. And I'll show the difference between using the 20,000 ohms per volt and the 1,000 ohms per volt. So 20,000 and 1,000 ohms per volt. And I'll show the difference that the reading comes up with because of the load or the burden that the meter places on the circuit. So to do the demonstration, I'll just use these two resistors that I already pulled. One of them is the 50K and the other one is the 500K. All right, so we'll make a simple voltage divider. We'll have the 500K and the 50K in series like this, all right? And we'll measure the voltage across the 50K so that the 500K is in series with the you could say B plus, or our positive power feed coming in. Ground will be down here. And the negative side will be on the bottom of the resistor. So just two resistors in series. We'll take a reading across this resistor and let's see what happens. I'll be back in a minute. Okay, I have the ME9HU multimeter in position for a demonstration on the 20,000 ohms per volt versus the 1,000 ohms per volt. So the circuit that I have hooked up is a 30 volts across two resistors in series. So this is a 500 k ohm resistor and this is a 50 k ohm resistor. So again, we have 30 volts across those two resistors. Jumper wire in the middle there is just joining the two resistors. So the fluke meter over here, we'll use this to take a couple of readings and then we'll compare them to this meter. So we'll start with the actual reading across from the power supply, and we see it's exactly 30.00. This resistor, 27.16, and over here we have 2.704. All right. So again, going back to that total, we have exactly 30. So let's take a look at that total voltage on this meter. So we're on the 20,000 ohms per volt direct reading. So the positive to the positive side, negative to negative side over here. And we do see it's exactly right on 30. So that looks very good. So this is on the 50 range because it's on the 50 jack. So on the meter scale, you have 5, 4, 3, 2, and 1, and then 0. We're reading on the black numbers on the DC scale. Because it's on 50, the 5 becomes 50, 40, 30. So again, if 30 is right there, no problems. It's very, very close, right on that 30 mark. Okay. Now, let's take a look what happens if we read across just one resistor. So this resistor over here, we're seeing 27.16 volts across that. They're not equal values, and two resistors in series that are not equal values will in fact divide the voltage differently across, or drop the voltage differently across each resistor. So we have 27.17, all right? So let's take a look when we measure with this meter, the ME9HU. We can see it's actually about 26, okay, 26. So it's a little under that 27. Yet if we come over here, it reads right on 30, which agrees with this meter. But on this one resistor, we see that it's a little bit of about a volt difference in reading, okay? So it's 25 right there, and then each tick mark is another volt, so 25, 26, okay? So why is that? Why is there a discrepancy? Well, as we recall, mentioned earlier in the video, the 20,000 ohms per volt, 20,000 times 50 is 1 megohm. So you could think of this meter right now as placing a 1 megohm resistor across this 500K resistor, and then we have a 50,000 ohm resistor over here. Well, that's going to change the voltage drop in the circuit. This meter has almost 10 times the input resistance, or almost over 10 times the input resistance or impedance on this meter. So this meter, when connected across here, is having less effect on the circuit. It's just that simple. Now, to show that in even a more drastic way, if we come over to the 1,000 ohms per volt, okay, as we recall, mentioned earlier in the video, on the 50 volt jack over here, this is only 50 k ohms of resistance. So it's like placing a 50 k ohm resistor across this 500 k resistor, right? Well, that's certainly going to change the circuit. So if we come over here to 1,000 ohms per volt, plug this in over here to the 50. And remember, we have 27.16, okay? But if we come over here like this, well, that's very, very low. I mean, that is a much, much lower reading. So at the 50, we're at 20, and then that would be 15. Let's see, there's 10, 14. So it's saying about 14 volts, looks like. All right, you can see right there, it was right on that tick mark. If that's 10, and that's 20, so 15 would be right in the middle, and it was about one tick mark down, so about 14 volts. Well, 14 volts is much different reading than we're getting with this meter. Flip the leads around like that just to keep the things correct there. So we have the 27.16. Well, again, has a much lower resistance on the 1000 ohms per volt. So that's something to keep in mind if you take a reading with this meter and you're using this. When do you want to use these jacks over here? Well, if a technical manual or something that you're reading requires, this type of an input impedance on your meter, then you want to use it. But typically you'd want to be using this side over here because this is simply going to load down the circuit further. However, if you come across the complete voltage source right from the power supply, go from here to here, very close to the to that 30 again, okay? So this is not wildly inaccurate in the meter. And why does this now read correct across the two resistors right from the power supply? Again, these two leads are coming right from the power supply. Well, the power supply, you could think of that as a very low resistance source, okay? Very low resistance. So if this is a 50k ohm resistor and you put a 50k ohm resistor across the power supply, the voltage drop across that resistor, the power supply is not going to be dropping any additional voltage within the supply. Particularly if you think of it as an ideal power supply, all of the voltage drops across the load. So placing this resistance across the complete circuit changes it very little, okay? Very little difference. Now, I've used this meter a little bit and I found that the 1000 ohms per volt in general, the accuracy on that, it tends to read a little bit low just consistently. So when you're going across there, the 30, it's reading just maybe a half a volt under, maybe 1 volt under the 30 mark. And that seems to be pretty consistent. I think that's just an error, percent error within the meter itself. But again, when you come across the resistor over here, you do get a very, very different reading because of that low input resistance. So something to keep in mind when you're using these meters. And again, the 20,000 ohms per volt is considerably a lower resistance than you would find with a modern digital multimeter, almost 10 times a greater resistance on the input. If you like this video, don't forget to give it a thumbs up. And if you're enjoying this channel, don't forget to subscribe. I'll be featuring more videos dealing with all things electronics. So thanks for watching, and until next time, goodbye.